when we first found derivatives, what we oftentimes would do is we define the derivative. So we defined it as the limit as h approaches 0 of some function. So this was the definition. So we'd have some sort of a plus h minus f of a over h. And we'd call this thing f prime of a. And what we were able to do is we were able to use algebra to be able to find the derivative at a particular point. But in this section, what I'm actually more interested in doing is finding some shortcut rules so that we don't actually have to rely on limits directly in order to find derivatives. So when we talk about basic differentiation rules, differentiation simply is a term that means to find the derivative. So you're finding f prime of x given f of x. So some of the basic rules that we use to find derivatives is that if we have a constant, so c is just going to be some constant or a number, the derivative of a constant is equal to 0. So just to give you an example, if we have f of x is just equal to the constant 3, so it's 3 at every single point, we can immediately conclude that the derivative of that function is 0. Now, this should make sense, because if we were to graph the function y equals 3, for example, you notice that this is a horizontal line. And regardless of what point you choose on this line, the slope of the line is going to be equal to 0. Remember, the slope of a horizontal line is equal to 0, and therefore the derivative is also going to be equal to 0. And this, of course, holds true for any line. So if we had, y equals 2, y equals, negative a half, any constant, the derivative of that constant will be 0. The other basic rule that we should also understand is that if we have something that is linear, so something that is already a line, that's going to be of the form y equals mx plus b, then the derivative is just going to be the slope of that line. Again, we should understand conceptually that a derivative is a slope. So if I were to take the line y equals 2x minus 1, and I wanted to find the derivative of that particular function, it's just going to be equal to 2. And again, if I were to graph 2x minus 1, the slope of the tangent line at every point is merely the same thing as the slope of the line itself. We can't really draw something that just touches at a single point. It will always touch at every single point. So I can just by observation notice that the run here is 1, the rise here is 2, so the slope is 2 over 1, or 2. Again, slope-intercept form will show you that that is true. So these are the two very, very basic differentiation rules, and they should be intuitive. Now, probably the most important rule in all of calculus that will be useful in this section and in almost every future section we do is the power rule. So it turns out that if you take the derivative of something that is of the form x to the power of n, this is just going to be n times x to the n minus 1. So just to do a couple examples of how this works, if I have something that looks like x to the 4th and I want to find the derivative of x to the 4th, the way I like to think about this is you take whatever this number is here, you bring it out front, so this is going to be 4x, and then you look at whatever this number is and you reduce it by 1. So this is going to be just 4x cubed. Again, we could also have used a limit definition to get here, but this makes things significantly more simple. It does turn out that this actually works for all real numbers. Okay, so for any value of n. So if I have something like the square root of x, we can actually use the power rule to figure this out. We do have to remember that the square root of x is the same thing as x to the 1/2, but we can still apply the power rule. The way we do this is, again, we look at whatever this exponent is, we bring it out front, so that's going to be 1/2. And then what we're going to do is we're going to take 1/2 and we're going to subtract 1 from it. So just as a reminder, 1/2 minus 1 is the same as 1/2 minus 2 over 2. or negative 1/2. And this will be 1/2 x to the negative 1/2. In many contexts, this is going to be an acceptable answer, but we can also reconvert it back into a radical. Remember that if you have a negative exponent, you can write this as a positive exponent, but you just place the function in the denominator like this, and then you can then reconvert it back into a square root. So this will be 1 over 2 square root of x. And actually, if you remember from the last example, a couple videos ago, we actually had the square root of x as one of our functions, and what we wanted to do is we wanted to find, I think it was f prime of 4, if I'm not mistaken. So the difference quotient there, and for this we can just plug that in, so that's going to be very nice. And just like we got 1/4 before, we can get 1/4 this way, and it's actually very easy. We can do an example here where we have a rational exponent. It's the same type of one as the last time. Notice we have a different variable, but it doesn't matter what variable we use. Differentiation is the same. We want to bring out this exponent, bring it out front, so that's going to be 5/4 t, and then we need to take 5/4 minus 1. And the easy way to think about this is that you're going to subtract 4 from the numerator here. So the numerator is 5, so that's going to be t to the 1/4. And that will be our answer. The next rule that's also very fundamental and useful is the derivative of the exponential function, which is the function y equals e to the x. It turns out that when you have a base e exponent, and only for a base e exponent, the derivative of the exponential function will in fact just be itself. This is not true for more general exponential functions like 5 to the x or 10 to the x. You have to do a little bit more work to get the answer, but for e to the x, it will just be e to the x. And just as a reminder, the value of e is 2.72, roughly speaking. It isn't a rational number, but it's about 2.72. As a side note, it actually happens to be the limit as n approaches infinity of 1 plus 1 over n to the power of n. So that's the exact value of e, just as a side note. So one other thing that's very useful about differentiation is that it happens to be what is known as a linear operator. So that means that it follows this particular set of rules. If you want to take the sum or difference of a derivative, it's going to be the derivatives of their sums. And then you can also pull out each of the corresponding constants. Now, this is something that you really don't have to remember this rule when you're dealing with finding derivatives. The key here is just to know that you can take derivatives term by term. So as an example, if I want to find the derivative of something like this, we can simply take the derivative in a term by term fashion. So because we have an x cubed in the denominator here, in order to apply the power rule, we have to move it upstairs. So this actually will become 2x to the negative 3. But we're going to actually pull everything out. So this is going to be 2 times the derivative of x to the negative 3 minus 3 times the derivative of e to the x, and then plus the derivative of 6. So we can just do each of these term by term. So if I want to find the derivative of x to the negative 3, again, we have to be careful here because we do bring the negative 3 out front here, but we need to reduce it by 1. And when we reduce negative 3 by 1, we actually get negative 4. So this is going to be negative 3x to the negative 4. And then this will be minus 3. The derivative of e to the x is just e to the x. And then we've got the derivative of 6. And if we remember from the beginning, the derivative of a constant is just going to be 0. So when we simplify this, this will become 2 times negative 3, or negative 6, x to the negative 4th, minus 3 e to the x. So as you do more and more of these examples, you don't actually have to bring this derivative inside for each one. You can just do it in your head, but it is helpful to know that we can take derivatives on a term-by-term basis. So that allows us to take derivatives of rather complicated functions like this in a relatively easy way. So that is all for this section. I hope that you found this video helpful, and as always, take care.